This is an excerpt from an unpublished video about the design of an ECM jog detector. A jog detector is a device attached to the target that measures seeker power and indicates seeker antenna pointing error by noticing jogs or dips in the seeker power measured at the target. Why bother with an ECM jog detector? Because it is by far the most important type of feedback necessary for cognitive jamming against current and future radar homing missiles, either by decoys or active onboard countermeasures. It is essential that the seeker antenna be peeled off the target in order to cause the missile to miss the target. A jog detector confirms or disconfirms that this is happening. Now, this video makes 3 points. Firstly, it introduces the idea of a jog detector operating regime. Key point. Secondly, the idea that different types of jog detector are required, each one for a different type of tests. And thirdly, that it is necessary to be very careful about how anechoic chamber tests and coaxial cable tests on a lab bench are designed and carried out, since it's very easy to make the worst kind of mistake, one that's difficult or practically impossible to detect. So here's the excerpt. Part 2, Simple Jog Detector Design. Now, perhaps the simplest jog detector is one based on measured seeker power rate. I'm not going to get into why that is, doesn't matter. Here's an example graph of measured seeker power level as versus range for a sea skimmer missile. And here's the corresponding seeker power rate graph. And here is the jog indication logic signal. Let's zoom in here.
So here's a key point. The graphs you're looking at right now show multipath only. There are no ECM-induced antenna jogs in these graphs. That means that everywhere the jog logic signal goes high is a false jog indication. Now, a correctly designed jog detector operated in its operating regime will not be fooled by multipath, and it will show no false jog indications, no jog indications at all in the data that you're looking at right now. But that's not what we have here, because a rate-based jog detector based on our seeker power rate is too simple. And the reason we proceed anyway is because the purpose of this video is to illustrate some principles.
Now, when the power rate is more negative than the threshold value, the jog indication logic signal is true and it's false otherwise. Notice how the width of the jog logic signal changes as the indication threshold is made more positive. Use of the jog logic signal, whether it triggers an action on the leading or trailing edge or elsewhere, is a separate issue that it's not addressed here. Now, once the power rate threshold has been chosen for recognizing jamming-induced angle errors, then the operating regime of the jog detector can be defined. It's defined by the engagement conditions under which multipath does not cause power rates, that can be confused with seeker angle deflections. And the word condition, in quotation marks, means specifically these things. Firstly, the missile speed and altitude flight profile. Secondly, the minimum range of the missile from the ship at which the jog detector needs to work. Thirdly, the sea conditions under which it needs to work. And fourthly, the range of radio frequencies covered by threats for which a jog detector is needed. Now, wiggling any or all of these parameters can change the graph of probability of false jog indication versus missile range, which is these graphs we've been looking at up till now. The operating regime is the combination of these 4 parameters for which the probability of false jog indication is sufficiently low, where sufficiently low means, well, we have to define that yet. And here's another key point. For different test conditions, we may require different jog detector configurations or even different designs to ensure that the detector's operating regime includes the real-world operating conditions, so the operating conditions where you need it to work. For example, as a first example, consider a jog detector whose intended use is in combat against a guided missile attack. Now, typically this might involve a high-speed missile or even supersonic missiles, both skimmers and divers in X-band, Ka band, and possibly Ku band. As a second case, consider air carry trials in which the aircraft necessarily flies at a slower speed and higher altitude than a real guided missile. It's possible and even likely that the aircraft will operate partially or entirely outside the operating regime of the 4-combat jog detector. Depending on the altitude and the speed, at long range the aircraft might operate within the detector's regime. In other words, the combat detector reliably detects jogs from the aircraft. That said, it might be possible to move the captive carry aircraft even farther into the operating regime of the jog detector, the 4-combat jog detector, not by flying faster, but by flying slower. What matters to the jog detector is the time rate at which multipath peaks and nulls are pushed through the jog detector's receiver. Peaks and nulls are spaced closer together by high altitude, so the only way to slow them down through the jog detector is to slow down the aircraft. Here's what it looks like. The missile flight is on the top, and a high-speed, high-altitude aircraft is below. See how much faster the peaks and nulls happen for the aircraft compared to the missile. Now here's a comparison of the same missile with the same aircraft, but the aircraft flies slower. The rate at which the peaks and nulls go through the jog detector is better matched. And a third difference, yet again, might be an anechoic chamber trial in which a real seeker is used, but multipath must be represented by an artificial model. If the multipath model doesn't match what the air carry tests provide, or what would be seen in a real-world combat, including missile speed, by the way, then a third jog detector is required. A fourth option might be a lab bench test in which the equipment is interconnected by coaxial tables. There might be a real seeker, but there isn't any free space radiation, so the ECM jogs must be artificially created by the software. And if those jogs are the same as what we see in free space transmission, fine. But if they're not, then you may need a different jog detector. If multipath is included in the coaxial cable tests, it also has to be represented by a model like the anechoic chamber case. So you might need different jog detectors for different applications. It's worth mentioning that there are two versions of the anechoic chamber tests which blend into the coaxial cable tests. There is free space radiation in the anechoic chamber test, but not necessarily for both the seeker and the jammer. In the first version of the anechoic chamber test, which is uncommon, both the jammer and the seeker radiate in the chamber. In the second, more common version, the seeker does not radiate, so free space radiation only comes from the jammer. Now this means that the real seeker antenna pattern only applies to the signal received from the jammer. And since the seeker does not radiate into free space in the chamber, the real seeker antenna pattern is necessarily not applied from the seeker to the jammer. This means that the seeker antenna pattern in transmit mode must be synthesized and fed to the jammer through coaxial cables. So from the point of view of testing the jog detector, there may effectively be no difference between the anechoic chamber tests and the coaxial lab bench type tests as seen by the jog detector. Now this genuinely opens the door to some spectacular mistakes that can undermine not only jog detection, but also the legitimacy of the whole engagement simulation for both the coaxial cable and the anechoic chamber tests. For example, suppose that the two-dimensional antenna pattern is conveniently synthesized using an azimuth cut, a single azimuth cut, and a single elevation cut of the estimated or the known seeker antenna pattern. The two-dimensional azimuth elevation pattern must be synthesized by blending the azimuth cut and the elevation cut of the antenna patterns to calculate the gains at angles which don't lie exactly on the azimuth cut or the elevation cut at intermediate angles. The correct way to do this is by circularly blending the azimuth and elevation patterns, but this requires a bit of math, not much, but some. An easy way to sidestep the math, though, is just to multiply the azimuth and elevation patterns. For example, the antenna gain at 2 degrees azimuth and 3 degrees elevation is simply the azimuth cut, the gain of the azimuth cut at plus 2 degrees azimuth, multiplied by the gain of the elevation pattern at plus 3 degrees elevation. Just add the azimuth and elevation dB gains at those respective angles, and you're done. Now, this innocent appearing shortcut produces two-dimensional antenna patterns which have a rectangular artifacts in it because they're caused by the application of the azimuth cut at all elevation angles and the elevation cut at all azimuth angles. And the resulting 2D pattern does not represent the intended antenna pattern, which, generally speaking, has an approximately circular symmetry. Result is, if the target lies off the principal plane cuts, then not only is the signal that's fed to the jog detector wrong, The skin echo is also wrong, and it can be wrong by a lot. A jog detector has an operating regime. The regime is the set of conditions under which the jog detector is unlikely to misidentify multipath as an ECM-induced seeker antenna jog. Now, the jog detector operating regime needs to be matched to the kind of tests that you're doing. Real-life combat, which is the ultimate test, or air carry tests, or anechoic chamber tests, or lab bench coaxial cable tests, or some blend of those. Each jog detector must be designed and configured so that the multipath that happens during the test is unlikely to be misidentified as an antenna jog. False jog indications caused by multipath, by the way, are not necessarily a showstopper. The effect depends on the system that's using the jog detector, and this study does not get into that part of the problem. Lastly, it's very easy to make errors when testing a jog detector. By that I mean it's very easy to draw incorrect conclusions when testing on a lab bench or in an anechoic chamber, or especially during air carry, in which the achievable aircraft speed and altitude may be outside the jog detector's operating regime. These are the type of errors that might be nearly impossible to detect and frankly have incorrectly discredited this technology for decades.